Hi, this is ET350, Lecture 17. Today we're going to look at an induction motor stator construction. In fact, this is very this would be relevant to a synchronous motor construction. Now, this lecture is going to go into a simplified version of the stator. They get much more complicated than this, but this lecture hopefully gives you a general idea of how we construct stators and how we take that three-phase electricity and get that spinning magnetic field. So we'll look at poles or poles per phase, groups, slots, and actually the slots equals the number of coils, and we'll look at coils per group. The last thing we'll look at is combinations of that you can build with when your slots and coils are 12. All right, so let's kind of break it down, look at some interesting cases. So remember, the stator is just, the outside of the stator is just a bunch of coils, right? And so I've represented these as a two-pole system with two electromagnets, right? So you have your rotor that can move around here, and then you have your electromagnet that's excited by AC current. So this is in your stator. And so this is an example of a two-pole system, 1 and 2, okay? Now, when you excite it with positive current, you might get something like this where the current goes down. If you flip the polarity, then the magnetic field will go up, okay? Now, what about one pole? Okay, so for one pole, well, it's kind of like one pole constructed, but remember, Gauss's law, number 2, is that you can't have monopoles. So it still behaves as if there's a south pole over here from the perspective of the motor, right? And so we have still that flux density going from north to quote unquote south. And we can call this one pole constructed, but we know that it behaves like two poles because no magnetic monopoles, right? Okay. What about a four-pole system? Well, in a four-pole system, you can see 1, 2, 3, 4. Notice they alternate north, south, north, south. Okay. So you would just have to know to flip it. And a six-pole would look something like this, where you have north-south alternating all the way around. Okay, so not too bad. This is just gives you an insight as to the number of poles that we will use in our equations and construction of a induction stator. So the phases, well, what does the phase mean? Well, we're already exposed to three phases. Each phase corresponds to a phase of current. Okay, a single phase has only one phase. So what's coming out of your wall is in fact single phase. So this is single phase AC current, right? Whereas when you get three of these offset by 120 degrees, you got balanced three phase, all right? Okay. Now, here's an example of a two-pole, one phase. Two poles, one phase, all right? So that's like this wall plug, you know, as the voltage supply, and you got two poles, all right? All right. What about a two-pole three-phase? Well, what you have is this. I know it looks a little complicated. We'll dive in deeper into, well, we've actually seen this before in the previous lecture, but we'll dive into deeper onto how these things are wound. But notice you got three phases, 1, 2, 3, and look at phase A. It's going to the A and it's like A prime, right? You got B, which is going to B and B prime, and C is going to C and C prime, right? So when we say poles, we really mean two poles per phase, or three poles per phase, or six poles per phase, okay? So it's poles, really poles per phase. Now, I have a note here, don't confuse this with a six-pole stator because of this same explanation. It's really poles per phase, right? Okay, let's keep going. Now that brings us to this next concept called groups, which is just the multiplication of poles per phase times the number of phases, okay? And so if you had a two-pole single phase system, the number of groups is 2, okay? Well, what if you have a two-pole three-phase system like this? Well, the number of groups is 2 times 3 times 6. And can you see this? 1, 2, 3, 4, 5, 6. You have 6 groups. We would call these groups, okay? Now, what about a one-pole three-phase system? Well, you would have 3 groups, right? Here's an example of 3 groups. 1, 2, 3. 3 phases, 3 groups, okay? One pole constructed, right? Okay, now you can imagine when this fires, you have a north pole here and the magnetic field flows out, right? You have your south, quote unquote. Same with here. If this fired with positive current, you'd have north coming out and a south, quote unquote, okay? All right, good. Okay, let's look at an example at a 4-pole 3-phase system. Okay, so number of groups is 12. 4 times 3, that's 12. Okay, and so how would that look? Well, remember 4 poles, which is really 4 poles per phase. So you'd have 4 alternating, A prime, A prime. And then you would have B prime, B prime, and then you have C prime, C prime. And it would look something like that. A prime, A prime. B, where's B? B prime, B prime, and then C over here, C prime, C prime. Notice that I have them offset by 1/3 of a cycle as best I can, right? Okay, good. So if you were to flip the synchronous speed direction or the magnetic field direction, you could literally flip how you've connected it into the motor, right? That's why flipping any 2 leads of a 3-phase motor flips the synchronous speed direction. Okay, and so you can see it behaves like if let's say you have 3-phase current coming out, you don't change that sequence. If you just connected the B and the C and you just flipped them, can you see how these coils would flip? Now, these letters correspond to coils, so don't get confused, right? All right. The other thing is you might be a little bit confused about the prime. Well, the prime just means that when I am exciting it with the same current, what you're getting is essentially something like that, where you're going south to north, and then see how we have north facing the south. Okay, it's like the complement. All right, good. Okay, so let's see how these things create a spinning magnetic field and how it alters the spinning magnetic field. The last time we looked at something like this, we had a 2-pole per phase system, and we had the same 3-phase balanced current. And we saw that when we had one electrical period cycle through, we would get 1 rotation of the magnetic field, but we only had 2 poles per phase in that system. In this system, we have 4 poles per phase. Okay, and what we want to do is we want to see what does the magnetic field behave like when excited by electrical frequency of this nature, where it's 3-phase balanced AC. Okay, all right. So what do I have here is something like this. Let's imagine that when I have my 4-pole per phase system, that if I were here at 1 and I excited with positive current, I'm going to have magnetic field leaving an A and entering an A prime. So the magnetic field would look like this. Sure, B and C and all that stuff are doing stuff, but let's just focus on the biggest current at a given time. So let's say the magnetic field looks like that. Okay. Now let's say we go to point 2. And at point 2, what do we have? Point 2, we have C, but it's maximum but negative, which means current's going to flow, or the magnetic field is going to flow out of C prime and go into C because we have a negative, right? So we're going to get something like this, slightly rotated. Now let's say we go to step 3 or time 3. We have B going maximum, right? When B is maximum, remember all these letters are coils and they're behaving like electromagnets. So now magnetic flux is going to flow out of B and go to B prime. Good. Notice how it rotates. That magnetic field is rotating a little bit. Okay, let's go to step 4. So step 4 is over here. What do we have? A, but it's negative now. So now it comes out of A prime and goes to A, right? Okay, notice it's rotated even a little bit more. I think you guys are getting the pattern. And then we go to C, which is now positive. So it's leaving C and going to C prime. Great. And we go to time 5, which is now B but negative. Okay. And it's flowing out of B prime going to B. Okay. And notice I put a little bubble here. You see that bubble is rotating. Good. And then what's next? We have back to A again. So after 7 of these peaks, we're back to the original position. But look at the bubble. The bubble, as you notice, didn't go a full revolution. It only went halfway. So that you can see that equation, omega S equals omega divided by P over 2, matters, right? Because now that we went from 2 to 4, we can see that it would require 2 electrical cycles, 2 of these electrical cycles to go 1 magnetic cycle, right? So there's a 2-to-1 ratio. All right, so this is upside down. Okay? So I hope this hits home this equation that the synchronous speed is related to the electrical frequency divided by the number of pole pairs over 2, or poles per phase over 2. Okay, all right, good, good. Okay, so now let's look at the number of slots. So this is the equation. The number of slots is the same as the number of coils you have, right? Which is the same as the number of poles times phase times coils per group. And don't forget, poles times phase is groups. So this makes sense, right? If you take groups times coils per group, you get coils, right? So the G's cancel, makes sense. Okay, so what is a slot? A slot is literally like a slot in the stator, okay? Right here you got 4 slots, right? What about here? You have a coil, literally a coil of wire, right? Now, what is a coil per group? Okay, it'll be a little bit more clear later, but a coil per group is just how many coils you have in one of those kind of chunks, right? And you can have more than one coil per group. And like I said, we'll see later. Now, why would you want more coils per group? You're going to get better starting torque, less noise, smoother, and however, it's more costly to manufacture. Okay. So let's look at some examples. If we have a 2-pole 3-phase 1 coil per group, we have 6 groups here. You've seen this already. A prime, B prime, C prime, right? 2 poles per phase, good. 3-phase A, B, C, and 1 coil per group. So there's only going to be 1 coil wrapped around it, right? Okay, what about if I had 2 poles, 3-phase, and 2 coils per group instead of 1? Okay, well, what we have here is we need to increase the number of coils and slots, right? Here we only had 6 slots and 6 coils and 6 groups. Well, here we would need 12, right? So what do we have? Let's see. We have 2 poles, 3-phase, 2 coils per group, a little double of this one. So we need 12 slots, 12 coils, good. And notice within a group, here's your group, you have 2 coils per that group, and 2 coils per this group, and 2 coils per this group. So within a group, we have 2 coils. Okay. Now, there's this concept called lap winding where you can overlap your coils, right? Even though you have multiple coils per group. And so an example is a student-built stator right here. So this is a 3-phase student-built stator with 12 slots and 12 coils, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I actually don't know if it's how many coils per group it is, but this is an example of how it's overlapping, right? Overlapping, right? Now that's not accounted for in these equations, the overlappingness, but this is an idea of where you're getting this kind of different configurations, right? And these equations are just kind of the basic equations. There's so many different varied motor designs that are out there. Okay, all right. You actually have motor trainers in your lab, and here's an example one. Same number 12, number 12. Both have 12 here. This one looks a little weird, right? You look at the rotor, and you're like, wait a second, that doesn't look like an induction rotor. You're absolutely right. This is a synchronous rotor. So what this guy is essentially, this is the other side. This you excite with DC current, right? And you create a permanent magnet that's fixed to this rotor, and this locks into the spinning magnetic field. And that's why this is going to be synchronous. A little foreshadowing to the future. Okay, these banana plugs allow us to kind of plug in and connect everything appropriately so that we can get these like 2-pole, 3-pole, 4-pole kind of nature. All right. Okay, good. So let's look at a little bit more detail of a 3-phase, 2-pole, 2-coil per groups situation. Okay, so what do we have? 3-phase, 2-pole, which is 6 groups. And if I multiply all 3 together, I get the number of slots, which is 12, and 12 coils. All right. So it looks a little bit crazy, but let's walk through it. Okay, 3-phase, A, B, C, good. Okay, 2 poles, which means I'm going to have like an A and A prime, B and a B prime, C and C prime. Notice the 3 phases are mechanically separated by 120 degrees. And if you were to make this work, these 3 phases would have to be electrically separated by 120 degrees. Okay. And then 2 coils per group. Look, here's a group here. And look, there's 2 coils. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So let's follow and trace out how we would connect this. So coming out of the A phase, the positive terminal, let's go to the A branch, right? And notice when I have positive current coming out of the A branch, I'm going to create a magnetic field that's going down. If I want two poles, this has to be my A prime, and look how it flows out of here into there. And in order to make that happen via my Ampere's law, I need to connect the end of this like so, right? And you can see that they're both, everything is in the same direction here, and then it can come back home. Does it matter if I went and connected this coil first and then this coil? No, it's all in series. Could you connect these all in parallel? You totally could. It would just change your impedance properties, but you would still get the same behavior of A and A prime. Now, what would happen if you flipped these or got these wrong? Well, you'd have like a north-south. It wouldn't work as well. You wouldn't get as smooth a spinning magnetic field when you excited this with your three-phase AC current. Okay. Well, what about the B? The B phase is just the same thing as how we connected the A phase, just rotated mechanically 120 degrees. So you can see how the A would go into here. Well, look at the B. We're going into there. Okay. And look how, if I were excited with positive current, look, we're getting a north going this way, just like we do with the A. And look how this magnetic field, if this was excited with positive current via our Ampere's law, we get north going this way, which is going to enter in here. And look how we have to connect it in order to do so, to get that right-hand rule to provide magnetic field to pull this in, right? And then we go back home. The C is the same thing. It's just rotated again another 120 degrees. So I come over here, boom, right? Come in to the side just like the B did. And it's the same thing, same pattern over and over, and I come back, okay? So again, this is an example of a 12-slot, three-phase, two-pole, two-coil per group situation, all right? There are definitely more complicated designs, definitely, right? This is just tip of the iceberg kind of stuff, okay? And if this is complicated, yeah, there's a lot more. All right, let's look at another one example. Here is a three-phase, four-pole, one coil per group system. Still, it has 12 groups. 12 is nice, right? 12 is actually a really nice number because of all the combinations. You have 1, 2, 3, 4, 6, and 12 that you can divide, evenly divide into 12. Okay, what do we have here? So remember, three-phase, good, 1, 2, 3. Four-pole, A prime, A prime. B, B prime, B, B prime, C, C prime, C, C, C prime. So this has 4 poles per phase, right? Okay, let's follow a line. So for A, let's just pick, we're gonna pick, if we have positive and we're having the A, we're gonna have north going in. That means this allows everything else to be dictated. If we want north in for this A, we want north in for that one. We want south for these opposites, right? Okay, so that means by Ampere's law, I gotta connect it so that the current goes this way around the coils and opposite here, and then into the rotor and then out of the rotor. Okay, so you can see that these 4 simultaneously will get triggered by A and create a magnetic field that does that, just as we saw. So we actually saw this one, with the spinning all the way around. Okay, what about for B? Well, B is just the same thing as A. This is A rotated 120 degrees. There we go. Okay. And it's the same thing, right? Look how this current is going this way. This one current is always also going this way, right? So I'm going to get a north here, right? And I should get a north here on the inside. Yep. I'm going to get a south here if I apply current. Good. And I'm going to south here. Good. And let's follow the line to make sure we did that. Okay. Going in. Good. Out. In. Good. Out, in, good, out, in, good, out. Now I want you to notice something. Look, for IA, I went into the A terminal first. For the B, I went into the B prime terminal first. Does that matter? No. As long as when I had current go in, it went in the right direction. I could have gone from the source into this terminal or this terminal or this terminal first. It wouldn't matter as long as I sent it in such a way that I got the current to go in the direction I want to get the magnetic field direction I want for positive current. Okay, I hope that makes sense. All right. The other question is, could I put these in parallel with these two? You totally can. Now, if you're going to do it for the B, you'd probably want to do it for the A and the C, just so that you have the same impedance values, right? Okay, so Just always have to be careful about your consistency. Now, what about C? Let's look at C. So the same thing here. Here's your C over there. If you excite it with positive current, we want a north. That's kind of our pattern for the A. So what do we have? North here, and then we're going to want a north here. So did I get that right? Right hand rule, good. Right hand rule, good. So north and north. What about for the C primes, which are on these sides? Right hand rule south, good. Right hand rule south, excellent. Okay, and so this goes, boom, all the way around. Okay. All right, so these are two nice examples of a 12 slot. One is a 4-pole, one is a 2-pole, both 3-phase, okay, that would work to create a spinning magnetic field when these are excited with 3-phase current that's balanced 120 degrees apart. Okay, kind of neat. All right, let's look at the last slide, which is just kind of an example of why 12 is so nice, right? What we're going to look at is combinations of the phases, the poles or poles per phase, and the coils per group. So let's say you only had one phase. Well, if you only have one phase, then what? Well, you would need 12 coils per group, right? That's kind of a crazy thing to think about, right? You'd have, let's think about that, right? One phase, this whole thing would be a coil in one big group. Yeah, weird. Okay, what about one phase 2-pole? Okay, 6 coils per group. Okay, so you could separate it right down the middle in half, right? And you could have like an A and A prime, and it would just make the magnetic field oscillate back and forth. Okay, what about 1-pole 3-phase? Well, then you would divide it into 3s, but still you would only get one phase out of this, right? Or you would only hook up one phase. 4-pole, kind of similar to this, right? Except everything is going to one phase instead of a B and C. Okay, six poles, I guess you could do that, and then 12 poles. Yeah, you could connect all these things. Not 100%, haven't done the analysis to see if all these would work, but what you would get with only one phase is essentially oscillating magnetic field. You wouldn't really get any rotation of the magnetic field. Okay, so would that work? Could you still get a rotor to spin, an induction rotor to spin? Well, actually, yes. So single phase may work if the rotor is kick-started. It might not work if it's sitting at a standstill, right? It'll just vibrate because the magnetic field in the induction is just going up and down, or in and out, in and out. But surprisingly enough, you might actually get it to spin in either direction if you just give it a kickstart. And a lot of, as we'll talk about later on in this lecture series, is that capacitor run motors are really 2-phase motors that start out as a single phase. And what happens is if the capacitor dies, you actually go back to a single phase. And then what happens? Well, one of the symptoms is that if you kickstart it, it'll run. So it's like it kind of runs, but it won't start up by itself. Interesting. Okay. So what about what if we have 2 phases? Well, these are all the combinations: 1, 6, 2, 3, 3, 2, and 6, 1. Okay. What is 2-phase? That's like having an A and a B. Now, this is actually how capacitor, like I just said, capacitor run induction motors work. And what they do is they electrically shift the B phase by the A phase 90 degrees, plus or minus. And so instead of a, 120, you'd get something like this. Here's your A phase, and then here's your B phase. Okay, and so they'd be shifted by 90 degrees. And what's interesting is you actually can get a spinning magnetic field. Okay, now what they also have to do is mechanically shift everything by 90 degrees to make sure that you get that rotating magnetic field. But it's kind of neat, right? Because you can imagine if I had a magnetic field north, and then it goes like this, and then it's going like this, and it's going like this, right? And really, individually, the phases are just oscillating back and forth, right? But it somehow does it. It's really cool. And we'll talk about the math that gets us there for a 2-pole system, or sorry, a 2-phase system. Okay. Okay. The next 3 are very happy. 3 phases. Yay. That's our standard 3-phase coming out here. We already did these 2 pole and 4-pole. Would this work? 1 pole at 4 coils per group, yeah, that would be like this chunk here is all connected to A, this chunk is all connected to B, this chunk is all connected to C. Yeah, I think that could work because you'd get this bang, 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 right? And so I believe that would work. Okay. And of course, the electrical sinusoids on these three would have to be 100 degrees offset. Okay. Now the last few are 4, 6, and 12 phases. Ooh, again, weird. Could you construct it? Sure. 1, 3, 3, 1, or 1, 2, 2, 1, or just 1 and 1, right? A little weird, but it might work if you properly offset the electrical phases, right? Four phases is like A, B, C, and D. This is add 2 more and add another 6 more on top of that. I think it could work. Imagine a different phase for the 12 phase for each one of these coils, and you could get this potential rippling effect if you offset the phases by 1/12. I think it could work, right? It would just ripple through and still create a spinning magnetic field. Maybe, yeah, it'd be fun if, and you could actually synthetically create multiple phases with an inverter, right? There's nothing stopping us from doing that now with transistor technology. Okay, so going to review, these are kind of our common ones for a 12 pole system. These could work, yeah. These definitely could work. These ones are a little weird, right? They're not self-starting, a little broken. These are definitely weird, right? These ones kind of are a default if this one fails, if the capacitor fails. So you can see that 12 is a nice number, right? Look at all the combinations you have available. But I hope at the end of the day in this lecture you saw briefly what the kind of inner construction of these stators look like. Okay, and like I said, there's definitely much more complicated stator designs than what I've shown. Okay, well, have a great day and see you in class.